Hi, it's Griffin, and back for the creating a command part of doing a command-based tank drive. So last time we did our tank drive subsystem, you remember, with our followers, configuration, we created our drive and our stop methods, got a few useful numbers, but right now the motors aren't really doing anything. The subsystem just represents that physical part of the robot, and the tank drive isn't going to move on its own. What you need is a command to tell it to move. The subsystem acts as the interface, the thing that can be told to make an action, but the command actually tells it to make the action. So inside of our robot folder, we're going to create a new folder. We're going to call it commands, just like we have our subsystems folder. And then we're going to right click, and similarly to how we made our subsystem, we're going to use this create a new class button, which will pull up this menu up here. You can type in command, none of these other commands, just the regular command. And we're going to name it tank drive command. Alright, so quick refresher on the parts of a command. You've got your constructor, like any Java class. This only runs once when this command is created. This is where you pass in your subsystem references, add requirements, and I'll show that on a little bit. This is initialize, which is only run once, but it's run once every single time that the command is scheduled. So that means every time that this command restarts, this part is run. So this is good for like resetting anything that needs to be reset every run. That won't be important for a tank drive though. Execute, that's like your periodic loop for the command, runs every 20 milliseconds. We'll be working with this a lot. Is finished tells the command when it should finish, when it should be done. And end happens after is finished turns true and can run stuff that you want to do when upon ending your command, like resetting. So let's start off up at the constructor right here. We know in this command we're going to need to set some speeds to our motors. And the only way to do that, because we don't have the motors instantiated in the command, our motors are instantiated here in the tank drive subsystem, we're going to need a way to link the two. So the way to link them is by passing in our tank drive subsystem as an argument. Right here, we pass in a tank drive subsystem, and we're just going to call it tank drive. And now, because we're going to need to access this tank drive subsystem throughout the rest of the command, because we're going to end up using its drive method, up at the top, we're going to need to create a local instance. We're going to create a private tank drive subsystem. We'll call it tank drive subsystem. Right here, standard Java stuff. Tank drive subsystem, this local variable is equal to the one that we passed in. You know the drill with setting up any Java class. Here's where stuff gets a little different though. We need to add a requirement. So add requirements is a WPILib method, and all it pretty much means is that no other commands can use this tank drive subsystem at the same time. Remember, in robot container, we created our one tank drive subsystem right here. I'm actually going to edit this name so it matches better. Tank drive subsystem right here. This is the only tank drive subsystem object. You should never be using new tank drive subsystem in any other place besides here. This one tank drive subsystem gets passed in as an argument to every command where we need it. Because there's only one, and there's only one set of motors, you don't want two commands trying to tell the subsystem what to do at the same time. What if you have one command telling the motors to go forward and the other one telling them to go backward? It's going to cause you issues. So add requirements blocks these commands in a way that only one command can be utilizing this tank drive subsystem at a time. So in our requirements, we're simply going to pass in tank drive subsystem to tell the command that this object can only be utilized here at a time. Yet again, you see, anytime we're talking about tank drive subsystem here, we're never using that new tank drive subsystem instantiation line. It's always setting equality, meaning that it's just a Java pointer to the tank drive subsystem that we created right here. Now, there's some more info that we need in a tank drive subsystem. How are we going to tell the tank drive to drive? So one way to do it would be to hard code a value into your tank drive command for a certain percent out for it to run, but that isn't very useful. You don't want your robot just going straight in one direction for the whole match. You want to pass in controller inputs like we did in robot.java. The way that you do that is another argument using not a double, but a double supplier variable. We're going to need a double supplier for our left percent and a double supplier for our right percent. So you might ask, why not just use a double to give the controller percents? Well, here's why. When you instantiate a Java object, this constructor is called. If you just use a double right here, then the value of left percent and right percent are going to be locked in to whatever that first input you gave it was. If the controller stick was held at 0.5 and then you constructed the tank drive command, the double passed in would be 0.5 and it would never change. We want that continuously updating input, and double suppliers can do that for us. All a double supplier is essentially an object holding a double. And if you remember something about Java objects, it's that Java objects can be pointed to in multiple places and can be changed in multiple places. So by using a double supplier, we can update that value from the joystick over and over again because it's the same object being used. And then we can access in this tank drive command the joystick value using the double supplier. So you might ask, why not just create the joystick in here, make our little joystick object, and avoid all this hassle? Well, that means that no other commands could use the joystick. By the nature of how these commands work, you're going to need your joystick in a central location that all commands can access it. So you can access all of the buttons, because each of these commands is their own class, unlike in robot.java. This all become clearer as I demo the process. So we're passing in a left percent and right percent, which are going to relate to our joysticks. And we have required that this command be the only one using our tank drive subsystem at a time. Now initialize. For driving, there's not a whole lot that we need to initialize. We're only going to use execute. So just like we did in robot.java, we're going to need to update our motor speeds. And remember, the way that we set this up in the tank drive subsystem was via the drive method. So all we need to do right here is type in tank drive subsystem. Remember, it's this one object up here that we're talking about, the one that was passed in and is passed around everywhere, our one instance of the tank drive subsystem for this whole code base. And we're going to use .drive. So using tank drive subsystem.drive, we're going to need to pass in some values, and those values are going to be based off of our double suppliers. Like I described before, these kind of represent our joystick values. So the way to access our double suppliers here is to store them locally as variables. So we're going to create a private double supplier left percent and a private double supplier right percent. And just like how we set our tank drive subsystem here, we're going to use this dot because they have the same name. Standard Java object creation stuff. So now these local variables in our tank drive command are pointing to these suppliers here. And then in our robot container, in the last step of this process, these double suppliers will hold the active value, the live value of a joystick. So coming back to execute, now that we have these saved, we're going to use them. We have left percent and right percent. But wait, why are we getting an error? It's because our drive takes in doubles, but not double suppliers. So you see, all we need to do to get the double value out of a double supplier is to use .get as double. So you might be asking, hey, you said that you need a double supplier right here to continuously update the joystick value. Why don't we need it in drive? We're using regular doubles. The reason is because drive is run in execute. Remember, execute is periodically called, which means every 20 milliseconds goes drive, 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 drive. And the drive then gets from the suppliers the most up-to-date value. So pretty much your subsystem's method to set your speeds doesn't need to use double suppliers, but the command needs to use double suppliers so that it can grab the most up-to-date info. So I know this can be a little bit confusing at first. Just remember, double variables need to be continuously updated. Double suppliers can hold a continuously updated value. Now, for good practice in our end condition, let's run tank drive subsystem dot stop. So that means that if this command ever stops, if we ever stop wanting to run tank drive command, let's say we switch to something autonomous, or we switch to some other way of controlling our tank drive using a command, then this command has to end. As we described before, there can only be one command utilizing the tank drive subsystem at a time. So we'll stop our drive, make sure the motors aren't spinning, because if they are spinning, who knows, that could cause issues. It's usually a good idea in your end method to reset your subsystems to whatever default state they are in, which for our tank drive we'll say is stopped and still. That's the end of creating our command. It's pretty short. But now we need to wrap everything up, link everything together. We have our subsystem that is the direct interface with our motors to control them. We have the command telling them what to do. But now we need to provide inputs to the command. We need to provide those percents. And where do we do that? In robot containers configure bindings section. So the first thing we're going to have to do is to create a controller. So if you remember, we commented this out earlier, but the command code starts off by default with having a pre-created command Xbox controller. So what makes a command Xbox controller different from our joystick object that we used originally? Well, it has easier integration with commands, as the name would suggest. As you can see that notes right here, you can use a command Xbox controller, or a command PS4 controller, or a command joystick if you're using a flight stick. I looked in recently, there's even a command PS5 controller, so they keep it pretty up to date. The cool thing with using a command Xbox controller, or the exact type of controller you have, is that if you have a off-the-shelf official Xbox controller, this will already have all of the buttons ID'd correctly inside of its code. You can see that for its ID, it takes in a operator constant K driver controller port, which was another pre-generated code snippet from this command-based project. We look in constants, that matches to 0. Let's make sure that in our driver station when we run, our controller is plugged in and in its slot 0. So moving on to configure bindings, this is where we configure our controller bindings. This is where you take any controller inputs you want and link them to your subsystems and commands. So the way we're going to do this for our drive subsystem is by using a default command. So the way that we're going to set up our tank drive command is actually by using a default command. Every single subsystem has the option of running a default command. That means that when no other commands require that subsystem, then this is the command that'll run. You can imagine that fits well for a tank drive because most always the tank drive is going to be what you're running. You're going to be driving around your robot like normal. So we usually set it as the default. This means that you don't have to remember to make sure it's running at any time. It just knows that if nothing else is happening with the tank drive, run that normal drive command. So then your driver can control your robot. So the way we do this is by calling our tank drive subsystem. Remember, that's referring to our one tank drive subsystem object, the one for the whole code base right here. We use .set default command. And the command that we want to set is a new tank drive command. So you see we're instantiating our tank drive command from right here. Remember that on instantiation, it's going to call this constructor doing all the setup and stuff. So that's what's going to run. And you can see that configure bindings is run on instantiation of robot container. And robot container is instantiated right when the robot is initialized. So this stuff happens pretty much instantly when your robot's code loads. So we remember that the arguments that we want for our tank drive command that we created right here are the tank drive subsystem being that one object from your robot container, a left percent and a right percent. So Java already had a good idea that we wanted to use this tank drive subsystem because that is our one object that we already have instantiated here. But now for left percent and right percent, we're going to have to fill those in. This is where you pass in those controller inputs that I was talking about before. This is where you provide a continuously updating value into that double supplier. So the way we go about doing this is not by creating a double supplier object, but by using a lambda expression. A lambda expression is typed like this: open parenthesis, close parenthesis, and then you type a little arrow with a minus sign and then a greater than sign. And then you need to reference your controller. So our controller is called m_driver controller. But now we need to actually give it a value. We use dot to look at all the options. And you can see, because this is a Command Xbox controller, it already knows the possible buttons. For our left %, let's use our controller's left Y, and then we can conclude with an open and closed parentheses, because this is a called method from the controller. So you can see that get left Y actually returns a double. And you might be like, hey, I thought you said doubles were bad. They don't update consistently. Well, because the nature of this lambda expression and the fact that this controller continuously updates with the new value, because a controller is always running when connected to your PC, the nature of this lambda is that it's pointing an arrow to this value. It's saying, hey, tank drive command, keep grabbing from here and put it into that double supplier. So in the end, this double supplier is utilizing this little lambda arrow right here and saying, hey, all right, I'm going to keep grabbing from this location. Now, we'll do the same exact thing for the right side. I'm going to copy this over, and instead we're just going to use get right Y. So you'll remember that this is the standard convention for driving a tank drive, where the left sticks up and down represent the left side going forward and backward, and the right sticks up and down represent the right side going backward and forward. So that means that if you press both sticks upward, the whole robot will move forward, and pressing them in other combinations can make it turn or go backward. But overall, this is how you set it up. But there's one last thing to check. Let's open up our driver station. So generally in our minds, a positive number is going to mean forward and a negative number is going to mean backward. If you think differently, well, I guess you can change up your code scheme, but that's the general consensus. We also assume that forward usually corresponds to pressing our joysticks upward. Just like in a video game, when you press upward, the controller goes forward. If you press leftward, the character moves leftward. So one thing that we need to verify is that our left Y and right Y being pressed upward actually gives us a positive number. Let's take a look right here. Rescanning for my controller, I can see that's active if I press a few buttons on the POV and also on the controller. Let's take a look. So if I press up our left Y joystick, look at that value. It actually goes negative. So upward on our left stick actually gives us a negative value, which would mean in our code, our robot would move backward. That's counterintuitive. Let's see if that also happens on the right y-axis. Upward on the stick also gives us a more negative number. And if I go downward on the right stick, it gives us a more positive number. So forward is backward and backward is forward. That's confusing. The simple way to fix this is with a negative sign. So if we know that our left Y going upward gives us a negative value, but we want to be passing in a positive value to our command, which then gets passed into our drive, which then right here applies to our motors, then somewhere in there we're going to need to flip it. An easy place to do that is right here. Simply place a negative sign right in front of both these values. Doesn't cause any syntax issues. It just means that our lambda arrow points, hey, all right, double supplier and tank drive command. Continuously grab from the opposite of this value. You can create a whole host of expressions that the lambda function is pointing to. So any simple mathematics like this work out well. Now we should have a fully functioning tank drive in the command-based framework. Let's simulate and see if it works. Let's grab our SimGUI. Alright, we can see on the driver station we have communication code joysticks, nothing crashed. That's great. Let's extend these printouts, then we can see how accurate they are. And let's enable. Now I'm going to press my left joystick up. Whoa, look at that. Our left drive % goes up. You can see that's very small values. You remember how we talked about the inaccuracies of Sim, how current limits can make it a little bit confused. And if I move the right joystick up, the right goes up. So I can move them both. Upward goes positive, downward goes negative. That all checks out. We have all of our motors connected. So now we can control a tank drive using a command-based framework. That's pretty awesome. So one thing you might notice is right now I'm not touching the controller and these values are not 0. You remember we talked about this in robot.java. You can have a little bit of issues with deadbanding. Let me show you where to put in a deadband in a command-based framework real quick. Let's disable. Going back into our code and stopping our simulator. A good place to apply a deadband is in the commands. You don't want to apply a deadband in your subsystem method, since this should be the most raw information. This should be direct communication with the motors. You don't want to deadband your direct communication of motors, since sometimes you might not want that deadband. Sometimes you might be controlling your motor using something very accurate that isn't a controller with deadband issues, like an autonomous routine, and you don't want to restrict that accuracy in an overarching manner. So, the place to deadband is in the tank drive command on these double suppliers. Just like we did in our teleop periodic, in the execute method instead here, we're going to create a double left percent deadbanded, and we're going to set this equal to math-util, using that wpilib library, dot apply deadband, with the value being left percent dot get is double, and the deadband being, usually on these controllers, I think we tested before, about 0.07. This value varies based on controller condition, quality, type of joysticks. Let's do the same thing again, but except this time for our right side, using right percent deadbanded, getting right percent double, and let's use the same deadband. Now we're going to drive using our new deadbanded values. So you can see now that we are deadbanding before passing into drive, so we get all the benefits of deadbanding our control, but drive is still free from deadband in case we want to control it without a deadband. Let's simulate again. Back in our simulator, I'm going to enable teleop, and you can see that it stays at 0 when I let go of my joystick, but when I move the joystick, it goes up. So if I press right and left, let go, it goes back to 0, down, goes back to 0. This is very good. This means that we won't have a robot nudging along even when we aren't touching our controller. So that pretty much concludes our tutorial on how to set up a tank drive subsystem in command-based. This may seem like a lot of work to do what you already set up in teleop periodic before, but in the long run, and once you get more complicated robot code, this allows you to create so much modularity. You can create so many different commands, control your robot in so many different ways. It allows you to have an overall more adaptable code base with more complex capabilities. There's still more to learn about command-based though. Keep watching the rest of this chapter to find out.